Hello friends. Now we will discuss about the relation, types of relation. In class 11, you have learned what is relation. Relation is a subset of Cartesian product, and relation we define numerically or non-numerically. Types of relation here, that is, one is reflexive. Reflexive, the term used in physics, that is reflection. So if there is an object X and its image, we consider this is a mirror. Reflection will be same X. So in reflexive property, when there is an order pair A comma B, we will make a relation between A and A. And if this belongs to the relation, then it will be reflexive. Say for example, a triangle ABC. We know it is always congruent to triangle ABC. So congruency is a reflexive relation. Any line is parallel to itself. So parallelism is a reflexive relation. Can we say that any line is perpendicular to itself? No. So perpendicularity is not reflexive. Now let us see another example here. Let A is equals to, consider that elements 0, 1, 2, 3 belongs to set A, and R is a relation defined by A divides B. So if we write the R, here 0 divides 0, 1 divides 1, 2 divides 2, 3 divides 3. So for all elements of the set A, we are getting these doublets. So we can say here R is reflexive. What about this one? A is equal to, A contains the elements 1, 2, 5, and R is a relation defined by R such that A to B, A is equals to B square. So clearly R will be reflexive if A is equals to A square is true for all elements, for all A belongs to set A. Now 1 is equals to 1 square. It is true. But 2 not equal to 2 square. 5 not equal to 5 square. Therefore, we can say here this R is not a reflexive relation. So we define reflexive relation as if A, A belongs to R for all A. So this is the important term for this. It should be true for all A belongs to the set A. So then R is said to be reflexive. I recall it should be true for all A belongs to the set A. In the previous example, we have seen that when we defined a relation A is equal to B square, it is true for this, but it is not true for all other elements. Elements of set A. Next relation, number 2, symmetric. A relation R is said to be symmetric if AB belongs to R, implies its reverse relation, that is BA, also belongs to R. For all AB belongs to the set where R is defined. Say for example, triangle ABC congruence to triangle PQR. So if we inverse the relation triangle PQR congruent to triangle ABC, is it true? Yes. Line A parallel to B, that is A parallel to B. Is it implied that B is parallel to A? Yes. So parallelism is a symmetric relation. Now let L and M are two lines. If line L is perpendicular to M, so we write L comma M. And if we reverse the relation, then the order pair. Now the question is, can I write L comma M is equals to M comma L? Yes, because if L is perpendicular to M, automatically we are getting that M is perpendicular to L. So the reverse relation is true. So we can say perpendicularity is symmetric, but it is not reflexive. Next, we consider another relation. Let R is a relation defined on set of integers z such that R is equals to x comma y and x minus y is divisible by 2, where x, y belongs to M, natural number. Now we have x, y belongs to R, means x minus y is divisible by 2. So can I say that y minus x, because x minus y, if I reverse this, minus of this is divisible by 2. Therefore, y comma x belongs to R. So R is symmetric. Now, transitive relation. Transitive is coming from transition. Here we are we'll do the transition A from B and B to C, and then we'll come to A to C. That means if A comma B belongs to R and B comma C also belongs to R, if this implies that A comma C belongs to R, then R is said to be transitive. Like A is less than B, B less than C, so you can say that A less than C. So is less than is a transitive relation. Congruency, or say similarity. Triangle ABC similar to triangle PQR. Triangle PQR if it is similar to X, Y, Z. So automatically this implies that triangle ABC similar to triangle X, Y, Z. So similarity is a transitive relation. Another example, that R is defined on the set of integers, and R is equals to x comma y such that x minus y is divisible by 2. xy belongs to natural number. So now the question is, here R is defined on the set of integers and R is equal to x comma y, x minus y is divisible by 2. That is x, y belongs to R implies x minus y is divisible by 2. Y comma z belongs to R. Y minus z is divisible by 2. This together implies x minus y plus y minus z divisible by 2. This implies, if we simplify this one, we'll get x minus z divisible by 2. So x comma z belongs to R implies R is transitive. Equivalence relation. A relation R is said to be an equivalence relation if R is reflexive, R is symmetric, and R is transitive. Example, similarity, congruency, parallelism, or equivalence relation. Okay, thank you. For testing your understanding of this lesson and more videos, log on to www.tubelessons.net.